Hi, welcome back to the book club. We're in chapter 7 of undergrad fluids, and this is actually a fun chapter for me. This is non-dimensionalization, and it's a pretty powerful way. Like a lot of times we might get caught up in all the equations, but a lot of times they can all kind of simplify to certain common phenomena. And so the way we'll sort of introduce this is, imagine you got a flow over, it can be a ball, golf ball, your pick, and this has got some diameter d, and then the flow going around this thing. So imagine that you've got some flow going around the ball, and there's some wake and things like that. Well, there's a velocity. The ball's traveling at some velocity v. So there's a velocity, and then the air's got some density and it's got some viscosity as well, mu. And so in the end, I'm saying the drag force. So we'll just say force, we know is a function of all of these variables. So it's a function of the diameter, the velocity of the ball, the density, and the viscosity of the fluid. And so we would start there, and then ultimately we want to essentially non-dimensionalize this and come up with how many different ways can they actually be treating each other. Now, the formal method, as you'll read in the books, called Buckingham pi theorem, and really, I'll just show you sort of an easy way to think through this. And really, we want to non-dimensionalize something, and I'll just keep this order. And so d raised to the a, v raised to the b, rho raised to the c, mu raised to the d. Okay? And so then we're going to look at the units of all this. And so what's the units of, we'll do this in green. What's the units of a distance? Well, it's a length. So basically, you'll see how I do this. That's a length. That's a length over time. That is a mass over length cubed. And then pascals, if you could work through it, I always forget. Pascal to me is, viscosity is a Pascal second. That's how I remember. That's a very more useful unit. I actually figure out what that is in its natural form. It is a mass per length and time. So it's like a kilogram per meter second. Okay, and so what you would then say is, okay, we're going to take a look at for length. Okay, we'll just count this up. So we have A plus B minus 3C minus D. And for it to be non-dimensional, that would be equal to 0. And so length and then time, if you do that, you'd have a minus B and then a minus D equal to 0. And then your mass. And over here, you just say it's C plus D equals 0. Okay, well, so this is, I can turn this around and say C is equal to minus D. I can turn this into saying that B is also equal to minus D. And so I can shove that back into this equation, and then you'll have A plus B. Well, that's a minus D minus 3C. Well, that's D. And then minus D is equal to 0. Or if you will, that should be A. I have a minus D. So plus 3 minus 1, A plus D is equal to 0. And then you kind of get a freebie. So if, you don't get a freebie, you're welcome to find this. So I'll just choose A equal to 1, which means D is equal to minus 1. And you put that all together. What is your non-dimensional variable? It is rho, because that's A. So A is 1. D is minus 1. And so B is 1. So rho V D over mu. And this is how we define Reynolds number. Okay, so that's our non-dimensional variable. And then if you repeat this for the force, okay, you're going to end up getting that the force itself will write itself as force over rho v squared d squared in that framework. Okay, and we would call this drag coefficient. And sometimes you got to pay attention. Sometimes I might do a half because rho v squared, if it's half, is dynamic pressure. So be careful with that. But then what you'll see is plots of this would look like this. Okay, and so this is, I know it's off the screen, so I'll just say this is drag coefficient versus Reynolds number. and comes down like this, and then it's got some sort of gap. In fact, normally this is plotted versus log of Reynolds number, and that's the flow over a ball. In fact, one of the reasons this sort of an interesting dip here has to do with changing of the wake. And so, one of the reasons a golf ball's got little dimples on it is actually to achieve that drag reduction right there. So that's pretty cool. Okay, so that's similarity. And honestly, there's a whole range of these non-dimensional parameters that we end up seeing. And so Reynolds number, this is one of them. And if you will, this is normally, you can describe almost each one of these. This is sort of the inertial forces, how the inertial forces compare to the viscous forces. That's the easy way to sort of think of Reynolds number. But there's a whole other, there's a Froude number, and you see this with boats, things like boat plowing through a two-dimensional surface, but it creates a bow wave, right? It's sort of gravity wave. And so Froude, ultimately it's sort of gravity versus inertia. And if I get that one right, that is the square root of the GL over V. There's a Weber number that's fairly common, and that one is looking at the surface tension. And so that one is inertia to sort of surface tension. And let's see, so that's a rho V L over sigma. I may have missed the unit on that. One we use a lot in high-speed flight is Mach number, and that's the velocity compared to the local speed of sound, A being the speed of sound, Mach number, of course, and then we did drag coefficient. And so there's a whole other sets of other ones. If you get into any sort of thermal problems, you'll have the Panton number, right, which is actually sort of the ratio of your viscous diffusion to thermal diffusion, and so that's a pretty common one. So there's this whole range of non-dimensional numbers that show up. And the reason we do that is actually all of our equations can be, with the right assumptions, can kind of simplify it down. And so you don't have to worry about changing density or changing size or changing different stuff. They'll have sort of self-similar solutions if things are right. And so, in fact, like flow through the air, for the most part, is the same as flow through the water. Now, that changes. Now, flow through the air is compressible. And so once compressibility effects become an issue, that would no longer be true. And so that would be, for air, to kind of pick a Mach number. So if Mach number less than 0.3 is usually considered incompressible. And so, if you're trying to look at, say, flows in a wind tunnel that are, your vehicle is trying to do Mach less than 0.3, well, you could also do the flow in the water tunnel. Maybe that's a cheaper or a easier option. So all of these things are pretty neat, but the formulas also have this really interesting reduction. So I'm gonna get into that here on kind of the right side as we kind of finish up this episode. And so if I write down up top, conservation of mass, and this is incompressible fluid mechanics, and so there you have del J Uj is equal to 0. That's right, divergence free. And then rho, and then we'll do time rate of change UI such t plus Uj. Of course, the rho has to be in front of that. Rho Uj del J Ui, and then that's the negative gradient of the pressure. And then this is usually viscosity, and then I'll just do del squared Ui. I do like the del squared as a compactness. You can write it just del J if you like. And so what you end up doing, kind of looking through the text, it would sort of recommend at this point saying, defining each one of these sort of variables, if you will, from a non-dimensional point of view. And so it would say, hey, if you have an x non-dimensional that put a star on it, you would say that's the x dimension divided by some length. And we'll just stick with, what we'll non-dimensionalize here is with some respect to some length, some u infinity, and density. That should be good. So we've got a length, we've got a time in the velocity, and then we got a mass, of course, in there. So I know that we could go through this math and figure it out, but I'll just show you how this collapses. Okay? And so velocity, non-dimensionalized, would be that velocity over u. I'll drop the infinity so it's not too hard. Non-dimensional pressure would be the pressure divided by rho u squared. The non-dimensional time, right? Because time is also a variable in here. You would look at that as time, and then you would have t, your velocity, right, divided by L. Okay? And so now we can come back through with this equation, and it gets kind of messy, but we've got all of our variables now defined. So expanding this out, I'll start over here to give myself some room. You'd have rho, and then honestly, what you do here is you look at this, you basically solve for ui. So this is the derivative of ui star u respect to time. Well, time, again, solve for time. That's t star L over u. And then you just kind of keep going. So plus rho, and then uj, well, that would be uj star times u infinity. And then I'm going to have to expand this out. So this is time d by ui star. So ui star u by dx j. Well, x is x star L. Right, solving for this one. Xj. And that's equal to, oops, lost my cap. That's equal to, this is del, again, pressure is P star rho U star by dxi, which is x star I times L, and then plus mu, and then this one gets busy. D, am I running off the camera? Too bad. Almost. I'll try to make this compact. You basically get x twice. xjl, there's a star there, d squared, and then, yeah, almost off the camera, xjl. Yep, and then velocity is ui star u. Okay, so now you collapse all the terms. In fact, I'll hop over to red here to kind of collapse the terms. All right, and so if you take a look at this, you'd have you get a u squared over L, and then all right, I'll just kind of write this. You get a u squared over L, looks like, out of this term. Looks over here. You got a u. There's another. So it looks like that's got a u squared over L. Come over here. Gosh, that looks like that's got a u squared over L. And then over here, there's a u over L squared. Okay, so what we'll now do is I'm going to divide by this whole thing then by rho u squared over L, and then see where that ends up. So what you're left with is then the time rate of change of ui star with respect to t star. Okay, great. Plus rho uj star, and then this is the derivative of ui star with respect to u xj star. Okay, perfect. Is equal to negative del p star over del x sub I star. All right, and then all of the terms basically finished up over here. So we had a u, and then I'll bring this one out. There is a u, and then, sorry, gosh, that was two L's there, if you will, two L's. And then I had to divide by the u squared, and so then you got a u squared over L, and then I'll just go back to this being del star, but I'll make sure it's non-dimensional, ui non-dimensional. Okay, what does that turn into? Well, that is a mu over, oh, and I forgot to divide by rho. Divided by rho, okay, there's rho. So I get a mu over rho. One of those, top L cancels with one of the squares, and top U cancels with that one. So that's a rho u L del squared ui, which you will then recognize that as Reynolds number. So 1 over Reynolds number. Perfect. And so then, if you kind of drop the stars at this point, that's what you would do in the world of fluid mechanics, drop the stars. And so basically non-dimensional fluid mechanics is this term with basically the Reynolds number. And so you may see this in a really compact form, which is basically the material derivative. Again, I'm dropping the stars, and just so people understand, this is now all dimensional. Negative del IP plus 1 over Reynolds number del squared ui. And so this was the sort of non-dimensional version of conservation of momentum. And then if you go back up here, this one's pretty easy. It's just, it stays the same, right? Okay, so it's because you got the 0 on the other side. So it just, you pull the constants out and you divide by 0 and you're good. All right. And so that's a non-dimensional equation. And so again, what's really nice is it allows you to not have to worry about what happens if I double the size of the ball, right? Or what happens if I do this in slightly denser fluid or slightly lighter fluid. Basically, the result here, this experimental result, is true. So you just figure out where you are in your Reynolds number. So if you double the ball, you double your Reynolds number, back to the definition of Reynolds number, which was here. And so you would double the Reynolds number. So you might go from here to here. Okay. And you're done. And so this really simplifies a lot of calculations, simplifies a lot of experimentations, a lot of results and things like that. And so the broader theory, it was just taught in this chapter, is Buckingham pi theorem. And so as you're going through some examples, you're going to get, kind of get some practice on this, of whether it's non-dimensionalized equations or, kind of solving for, hey, what are the variables that you should solve for? And so this gets pretty powerful. And so even later on, as we get into other chapters, especially when we get back into Panton, he's got a really good way of sort of taking a look at the full sort of fluid equations with all that compressibility, and then we'll then try to non-dimensionalize all of this stuff. We'll have all of these different pieces, and so it'll be really more clear to say under what conditions does fluid mechanics truly stay in this incompressible world, where does it start breaking? And there are actually some really interesting ones in between where, hey, you may still be considered incompressible, but you have to worry about a little bit of buoyancy. And so there are some really interesting regimes you can pop into, but it's all ends up being related to these numbers. So this is, again, where kind of the power of mathematics is important. And so, I do appreciate this kind of being in that undergraduate fluid mechanics, but having taught this course many times, this is one of those chapters that students usually kind of stumble their way through, or truly don't get, you truly don't get the power of it, honestly. And they just sort of understand, okay, there's a thing called a Reynolds number. Yes, okay. But really, it's much broader than that, much more important than that. And this is true. Honestly, this is true in basically all of physics. We always have these sort of non-dimensional numbers that sort of tell us what regimes we're in, because they see different flavors, right? Even boats, to go back to like Froude number, there are certain Froude numbers where wakes change depending on the speed of your boat or different things like that. It's pretty cool. So, all right, that's it for this episode, and we'll see you next time. Remember, like and subscribe if you're liking the series. Thanks.